Alrighty. So, 50 shades?
Please.
What? You didn't get notes? Oh, right, because you came in after I was done handing out. Okay. So, here we go. We're talking about we're talking about, or we're going to move into a topic that you may vaguely remember from pre-calculus, right? Parametric and polar equations, all right? So we're going to be covering parametric, of course, first. Then we're going to do polar, okay? The good news is that today we're not going to do any calculus.
Thank God.
We're just going to refresh what a parametric equation is. All right, we're going to refresh what a parametric equation is. So, this can be troublesome for some students because it kind of like, you have to like shift your thinking a little bit, something that we've been doing since probably elementary school, right? That is graphing, in the xy coordinate plane using just x's and y's, but now we throw in this parameter t, okay? So let's just kind of go through things here and then we'll kind of, show you what's going on. So, definition of a plane curve, P-L-N-A-N-E curve. I would say circle, put a question mark there, and then I'll check it, and I'll figure that out, yeah. So a plane curve, if f and g are continuous functions of t on an interval I, then the equations x equal to f of t and y equal to g of t are called parametric equations, and t is called a parameter. Usually, that parameter, t, is measuring time, so that's why we use t to represent it and stuff like that. Okay? So we introduced this new idea, right? X and Y help us normally determine a position, but of course, we don't occupy the same position, forever, right? In real life, right, we tend to be in different positions at different times. And so our X position, our Y position, in real life, or for other objects, not just us, tend to depend on what time it is as well as where our position is, right? And so that's why we introduced this new idea called a parameter to kind of help us, model that. All right. The set of ordered pairs xy obtained as t varies, okay, because now we're going to think about time varying, and then that time being our independent variable, and then x and y now kind of become dependent on that time. And so as our time varies, all right, and we kind of graph the position as time proceeds, we're going to call that the graph of the parametric equations. Okay, and then taken together, both the x and the y coordinates, and we connect those dots to the x and y coordinates, along with the times at which those things happen, okay, these equations then create what we call a plane curve, denoted by C, okay? We don't use the word function anymore because these graphs might not be functions, right? They might not pass the vertical line test. So we're going to call it just a plane curve, a curve that's in the two-dimensional plane, the Cartesian plane there, all right? This essentially allows us to determine where the x and y coordinates are over time through that new variable t. All right, so first thing we're going to do here is just example one, we're just going to sketch a curve. All right, no calculus involved. So if you again remember back to when you first learned how to graph things, using a table is probably where you started, right? You chose your x values. Why? Because at that point the x value was independent, and then you found the matching y value with it because the y value was dependent on the x value. Well, now t is our independent variable. It is the value that we kind of choose, and then x and y, since they're both functions of t, they depend on t, and so we then have to come up with values, that match those particular t values there. Okay, and all it is exactly what we've done in the past, where you take your your t value and you plug it in for x. So -2 squared is 4, -1 is 3. Right, and then you take your t value, same t value, -2, plug it in here for the y function. So 2 times -2 is -4, plus 1 is -3. Okay. Now, how do we graph something that has 3 numbers attached to it, right? Well, in the coordinate plane, we're still going to be using our x and y axis. All right. And we can still then locate the point 3, -3, as we normally would. So 3, down 3, there it is. Okay. So this point gives us the xy coordinate, but then how do we denote what time this happened? Well, you're just going to label the point. Okay, we're just going to label the point t equals -2. All right, and so there's our first point. All right, that's it. So we'll just keep going. Same procedure here. So we'll plug in -1. -1 squared is 1, minus 1 is 0. -1 times 2 is -2, plus 1 is -1. Okay, 0 minus 1 is -1. 0 plus 1 is 1. 1 minus 1 is 0 again. 2 times 1 is 2, plus 1 is 3. And then 2 squared is 4, minus 1 is 3. And then 2 times 2 is 4, plus 1 is 5. And we'll just plot then all these points. So 0, -1. That's going to be t equals -1. -1, 1. T equals 0. 0, 3. 1, 2, 3. And 3, 5. 3, 1, 2, 3, 4, 5. All right. And we want to connect these dots, right? So we want to think that, okay, well, just like there's t values between -2 and -1, right? So we could have chosen, for example, to evaluate t of -1.5. We would ideally then get an x and y value someplace between these two, right? So the idea is that we can still kind of connect the dots here, right? There's t values between -2 and -1, so there's then matching x and y values for all those t values between there. And the idea is when we connect these dots, we create a continuous graph. Okay, I'm not going to extend these. I'm not going to extend these and put arrows on the ends, okay, just because, I don't know, this is what we've got. Okay, I don't want to, I don't know, whatever, extend them. We're just going to leave them with what we've got right here. All right. An additional component here, though, is because we're going kind of proceeding through time, we kind of want to, indicate that, and so we have what we call the orientation of the graph, and that's where you just draw arrows to kind of indicate the direction, the flow of time. Okay, as time flows on, the particle or the object or whatever this thing is representing moves in this path. Okay, starting at time t equals -2 up to time t equals 2. Again, it's not necessarily time here, but that's that's one of the easy ways to kind of imagine it. All right, so questions on any of that? Okay, is this like ringing a bell from pre-calculus maybe? Nope. Nope. All right, very good. Well, if you had me for pre-calculus, we definitely did do this, but you might not remember, so you can still blame your pre-calculus teacher if you'd like. If you didn't have me for pre-calculus, well, you can't blame me, sorry. All right, so the importance of parametric equations is usually found in time and speeds, right? We already discussed that. So here is a good example of how speeds can be determined/manipulated. Okay, and so again, we're just going to sketch the curve here. Yeah. I'm not sure. Yeah, all right, well, anyway, I'm not really sure where I'm supposed to go with that, but there it is, all right? So we'll just continue on and graph this next one here, all right? So again, we'll plug in some of these t values and get their matching x and y values there. So -4 squared, 16. 1/4 of that is going to be 4. Minus 1 is going to be 3. And then -4 plus 1 is -3. -2 squared is 4. 1/4 of that is 1. 1 minus 1 is 0. -2 plus 1 is -1. -1 squared is 1. 1/4 minus 1, -3/4. And then -1 plus 1 is 0. And then 0, that's easy. -1 and 1. And then t equals 1. 1 squared is 1. 1/4 times 1 is 1/4. Minus 1 is going to be a -3/4 again. 1 plus 1 is 2. 4, 1, minus 1, 0. 2 plus 1, 3. And then 4 squared, 16. 1/4 of that is 4. Minus 1 is 3. And then 4 plus 1 is 5. All right. So let's go ahead then and plot those points and give the orientation and stuff like that. All right. Plot those points and give the orientation there. All right, so we plot this, and let's see here. You get 3, -3, 0, -1, -3/4, 0, so like roughly there. -1, 1, -3/4, 1, 2, 0, 3, and 3, 1, 2, 3, 4, 5. Okay. And again, I'm not going to like label all these here. I'll just do t equals -4 to t equals 4 here. Okay, and there's the orientation. What do you notice about this graph? Bless you.
It like got short and choppy.
Got short and choppy. Okay. What do you mean by short and choppy?
Like slowed down here. T equals -1 to 1.
Ah, okay. So it's slowed down. Now that's an interesting thought. We did actually slow down here. Okay. Let's compare these two parametric graphs that we just did. How do they look?
The same.
They look the same, right? So we're covering the same ground, but Mario's exactly right. We're doing it in a slower fashion here, right? This was from time t equals -2 to time t equals 2. So we covered this ground in 4 seconds. Okay, right? We cover the same ground here from time t equals -4 to time t equals 4. So that is 8 seconds. Okay, right. And so we covered the same space, but in different amounts of time. And so this is an example, kind of like how the speed of our parametric equation can kind of be manipulated, okay, and / also determined, right? We cover the same amount of ground, but in 8 seconds opposed to 4 seconds. So saying it went slower is exactly right. Okay, so very good there. All right. All right. So then. Let's talk about eliminating the parameter, right? So no sooner do we learn this new thing, but then we learn about how can we get away from it and go right back to our good old friends y and x and get rid of that t, right? So that's what we're going to do here. We're going to convert. So because parametric equations are kind of in the same universe as our functions and things like that potentially, right? Or relationship with x and y, we can kind of like translate from one universe to another. So we're going to translate from parametric now into our normal kind of what we call rectangular coordinates, right? So our old coordinate system, rectangular coordinates, new coordinate system we're talking about now, parametric equations, okay? So we're going to take, the goal here is to take these two functions, x that depends on t and y that depends on t, put these two things together and create a y equal to f of x. So now y, so relate y and x, okay? Eliminate that parameter. Okay, so here's our set of parametric equations, right? The goal here is then to solve for t in one equation, all right? Which equation should we probably go with here? The x one, right? It's super easy to solve for t in that one. So we get t equals 2x. Then we're going to take that t, which is equal to 2x, and we'll substitute it into the other equation for t. So now we're going to put in 2x quantity squared minus 4. So you get y equals 4x squared minus 4. Okay, and that's our equation. Okay, so this will give us the correct shape of our graph, right? It will match the shape, but it will now eliminate the idea of speed or time, right? We don't know like how quickly these things are happening. We just know that this is the pathway that it will take, but it doesn't tell us with respect to what time, how much time has elapsed in order to do that. Okay, so we've lost that aspect of it, but we can still at least get the right shape. All right, so example 3 here, let's rewrite the following equation in parametric form. So we're given it in parametric form, and we're going to rewrite it in rectangular form. All right, so again, for this scenario, all right, which equation should we try and solve for t? The first one here or the second one here?
Second one.
We want to solve the second one for t? All right, well, let's try here. So we'll multiply the t plus 1 times y equals t. All right, so again, I just multiply both sides by t plus 1. Let's see, here we get yt plus y equals t. All right, so I'm going to subtract yt from both sides here to get the t's together. All right, I'll factor a t out. And we can divide the 1 minus y over, so we get t equals y over 1 minus y. So yeah, this works. It works. Okay, we can then take that t equals to y over 1 minus y, and we'll plug it in for the t in the x function there. So x equals 1 over the square root of y over 1 minus y plus 1. Okay, so now we have x as a function of y, but we've accomplished what we wanted to accomplish, right? We can, we now have it in rectangular form. It's not our traditional rectangular form. Normally we want y in terms of x. But when it comes to the rectangular equation, you actually have the freedom to have it, either as y equals a function of x, or you can write it as x equals a function of y. Okay. So I don't know if I really want to simplify any further from there. I guess I could. All right, I'll do it. So we'll get. Let's see here. I want to get rid of this square root, so I'm going to square both sides, make it x squared equals 1 over y over 1 minus y plus 1. Okay. And then let's see here. I'm going to multiply this quantity in the denominator on both sides, and then also divide both sides by x squared. So I'll get 1 over x squared equals y over 1 minus y plus 1. Okay. And then, to get the y by itself here is going to be a lot more work. All right. I'll just put a dot, dot, dot there, because I don't want to spend too much time on this. But I do want to show you that if we actually had solved for x, if we solved for the t in the x equation first, it would have made things a little bit easier for us. So let's compare that here, solving this one for x first. If we multiply here, we get x square root of t plus 1 equals 1. So again, I just multiply that root t plus 1 over to the x. Okay. And then we will we'll divide both sides by x first. We'll do it that way. Okay. Like so. And then we'll square both sides, and so we get t plus 1 equals 1 over x squared. And so then t equals 1 over x squared minus 1. Like that. All right. And then we can substitute that in place of the t's over here. And so you get y equals 1 over x squared minus 1 over 1 over x squared minus 1, but plus 1. So we get 1 over x squared minus 1 over the minus 1 plus 1 cancel, and we have minus 1, or over just 1 minus x squared, or 1 over x squared. Right there. Okay. And if we multiply the top and bottom by x squared, okay, which we can do, right, because we're just multiplying by 1. If we do that, then we'll end up with 1 in the denominator. We'll end up with 1 minus x squared in the numerator, or just 1 minus x squared. Okay, so there's an easy way to see that. And believe it or not, this one over here should simplify to the same thing as y equals 1 minus x squared if we continue solving for y there. So yeah, Kara.
How did you know the part of the to solve for x in the first one versus the second one?
So how did I know that I wanted to solve for use this one to solve for the t as opposed to this one? I think the idea here is because in the first one you have a single t, whereas this one's got 2 t's. And so that makes it a little bit trickier to solve for t when you have more than one of those. If you have just a single one, it's easier to get that one t by itself. Because we have to, in this one, we have to first get the t's together and then start solving for the t, right? So that makes it more complicated. So in general, you want to kind of go for the one, if you're trying to rewrite in rectangular form, go for the one that has a single t in it. Okay, it's a good kind of strategy there to utilize. All right, so there's that. Any other questions on that? All right, let's continue on here. So now we're going to rewrite the following equation in parametric form into rectangular form, and then sketch. All right? So let's do that here. Now you'll notice here, in this case, our parameter has changed. Our parameter is now theta. Okay? Our parameter is now theta. All right, but it's still just like t. Okay, just like t, we're going to use that. Okay, so let's just choose, I don't know, let's just solve for the x here. So we'll say that x equals 5 sine theta. Okay, we'll get that theta by itself. So what should be our first step here to start solving for theta? Divide by 5. And now it should be our next step. Very good, right? We need to get rid of sine. We're not going to divide by sine. Dividing, this is not sine times theta, it's sine of theta. To undo sine of, you need to do arc sine, both sides. So it's arc sine of x over 5 equals theta. Okay, and then that theta, right, is the same here as the y equals 5 cosine theta. So we'll do y equals 5 cosine of the arc sine of x over 5. Okay. This is something we also saw in pre-calculus, if you remember, right? If you don't, I understand, because it's kind of like this weird little offshoot thing that we do. Okay. We can actually evaluate this, or simplify it, I guess I'll say. All right. If you guys remember, or if you don't, I'll say it anyway. All right. To solve this, we set up a right triangle. All right. And we set up a right triangle that kind of illustrates this relationship right here. Sine of theta equals x over 5, right? We want to evaluate first what the arc sine of x over 5 is, or what it represents, right? And so arc sine of x over 5 means there's some angle theta that when you take the sine of it, you get x over 5, right? That means the same thing, right? Arc sine of x over 5 we got from this, which is backwards we got from this, right? So these are meaning the same thing, okay? So we're going to put theta in our right triangle here, okay? And then according to sine of theta, what does this opposite leg have to be? X, right? Because the ratio for sine is opposite x, opposite leg, over the hypotenuse of 5. So that means the hypotenuse here is what? 5. Okay? And then by using Pythagorean theorem, 5 squared has to equal x squared plus, and then whatever this mystery is right here. So we'll say like mystery squared. Okay? So mystery squared is 25 minus x squared, or the mystery is just the square root of 25 minus x squared. Right? And so this mystery side here is root 25 minus x squared. Question? Oh no, Matthias is just stretching. Never mind. I was a little trigger happy right there. Sorry, Matthias. All right. So, why do we do all of this? Well, arc sine of x over 5 is theta. It's equal to theta. So when I take the cosine of the arc sine of x over 5, I'm really just taking cosine of theta in other words, right? The same thing as arc sine of x over 5 is theta. So if I take cosine of theta, I'm going to be able to evaluate this just as if I'm evaluating cosine of the arc sine of x over 5. What is cosine of theta? Root 25 minus x squared over 5, the hypotenuse, right? Adjacent leg to the theta over hypotenuse 5. So this is equal to 5 times root 25 minus x squared over 5. The 5 from the lead coefficient there. Oh, sorry, not. There you go. Yes, it is cosine. Cosine is adjacent over hypotenuse.
So you wouldn't have to write cosine.
No, yeah, the cosine goes away because we evaluated cosine of theta. It is this ratio. Bless you. Okay? And then the 5's cancel, and so we're left with that y is just the square root of 25 minus x squared. But if we square both sides, we get y squared equals 25 minus x squared. And if we add the x back over, it's a circle.
Oh my god.
Oh my gosh. It's right.
It's magic.
Mathemagic.
I just get worked up.
All right. So, let's go here now and graph this. Okay, let's graph this, right? So it's a circle with center where? At the origin with radius? 5. Very good. Remember, that's r squared. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Now, that's one way to kind of come up with a rectangular equation there. An alternative way to kind of come up with that equation, well, I'll show you here in just a second. But we're going to do the table too. I also want to do this parametrically as well. All right, so let's set up our parameter there, theta. Let's put our x here and our y here. Let's just make sure that our parametric equations would also give us the same thing, right? Ugh. All right, so we're going to pick values of theta between 0 and 2 pi. My recommendation, since we're going to be evaluating sine and cosine, let's use some easy ones like 0, pi over 2, pi, 3 pi over 2, and then 2 pi. All right, so sine of 0. 0 times 5, 0. Cosine of 0, 1 times 5 is 1. Okay. Pi over 2, sine of pi over 2, 1 times 5, 5. Cosine of pi over 2, 0 times 5, 0. Okay, we'll plug in pi. Sine of pi, 0 times 5 is 0. Cosine of pi, negative 1 times 5 will be negative 5. Whoa! All right, 3 pi over 2, sine of 3 pi over 2, negative 1 times 5, negative 5. 3 pi over 2 and plugged in here. Cosine of 3 pi over 2 is 0. Plugged in times 5 is 0. And then 2 pi, well, that's the same as 0, right? For cosine and sine, so we're going to end up with the same result. All right. So let's plot this first point. 0, 5. 0, 5. That is this point. All right. Now this is a little bit weird, right? We're saying this point here is theta equals 0. But wait, Mr. Witt, isn't this pi over 2? Right? It's right angle. I mean, so according to the unit circle, yes, this is pi over 2 away from our kind of like terminal side here of an angle. Okay, in the unit circle, that would be pi over 2. But remember, this theta here is a parameter. It's like t, so it's more like trying to represent like time almost or something like that. All right, so at theta equals 0, or you could think maybe at time equals 0, right? Our particle, our object here is at this position. All right, so don't get get confused here that this is theta equals 0. Okay, this is just the parameter theta. It's not necessarily describing this angle here on the circle. Okay, that's pi over 2, right? All right, so then pi over 2 is at the coordinate 5, 0. So pi over 2 is at 5, 0. So 5, 0 is right here. So which direction are we going? This way. You do know the way. It is clockwise. All right. And then pi, 0, negative 5. All right. So that's theta equals pi. And then theta equals 3 pi over 2 will be over here. And then finally 2 pi will be at 0, 5. All right. So we are going clockwise here around our circle. All right. So, again, let me show you one alternate way to think about how we can convert this into rectangular form. This one's a little bit trickier. Well, I don't know if I want to say trickier. Never mind. You guys probably think this one's really tricky, right? But anyway, let me just show you here. If we have x equals 5 sine theta, this method will be helpful for later when we talk more about polar stuff, I think. 5 cosine theta. Okay? I'm going to do something a little bit funky here. I'm going to solve both of these. So I'm going to have x over 5 equals sine theta. I'm going to have y over 5 equals cosine theta. So again, this is an alternate way to kind of come up with the rectangular coordinates, to eliminate the parameter. All right. I'm now going to square both sides. So x squared over 25 equals sine squared theta, and y squared over 25 equals cosine squared theta. Okay, now, we know something about how sine squared and cosine squared theta relate. Specifically, well, if they divide, it would be tangent squared, sure. But sine squared theta plus cosine squared theta equals what? 1. So sine squared theta plus cosine squared theta equals 1, that Pythagorean identity. But, oh, what do we have here? Sine squared theta is x squared over 25. And what do we have here? Cosine squared theta, oh, that is y squared over 25. And then if I multiply both sides by 25, it's the circle. Okay, so that's an alternate way to kind of like eliminate the parameter. Okay, that doesn't follow our typical method of like substituting and plugging stuff in and stuff like that, but it works as well because of that relation between sine squared and cosine squared. Okay, questions on any of that so far? So again, this is, I mean, not that you guys really care maybe, but for me, when I was in calculus, I can remember, and maybe that's why I turned out to be a math teacher, right? So you guys are all just like tuning out right now because, anyway, but you know, when I saw stuff like this, and just like, it was like really cool how I thought calculus brought together like everything that we've done up to this point, really, right? We have like geometry, we've got pre-calculus in here, right? This weird thing we learned in pre-calculus, like why are we even doing this? Well, it shows up here in calculus, right? So it's preparation, right? It was pre-calculus to get you ready for stuff you're going to be seeing later. The AB students don't get to see this. The AB students don't get to, you know, feel that, you know, like, we used it, you know, kind of thing.
See what calculus is involved with all of this.
Ah. Okay, moving on. So, why don't you guys go ahead and do this one. All right, we're going to go from -3 to 3. Okay, that's fair enough. From -3 to 3. Okay, and we're going. Let's count by ones, right? So we'll do again a chart, a table here. If you don't want to do it, that's fine. I'll just do it right now.
I'll do it.
All right.
Reluctantly.
Reluctant. Okay. So again, we're going to go from -3 to 3, and we're going to just count by ones. All right. Yeah, there are some fractions here, so let's see here. Yeah, this is what I want to do. All right, I'm just going to put the numbers in here. 2, 0, 2.5, 0, -2,
It's a circle.
There's some like circly aspects to it, I would say.
Close to it.
I like a cooking show. I had a pre-prepared example in the oven, ready to pull out to show you what it looked like. So here's some things to help you, right? So let's just say you didn't want to have to do all these like multiple calculations over and over again, right? One option you have is to use your calculator, right? So to use your calculator, you could stay in rectangular format, right? You can type the two equations into your y1 and y2. So I can do 0.5 x to the third minus 3x, and then I can do x squared minus 4. And then when I go to my table, I already, those are old grades, I already have my table set up to ask for my independent variable, so that way I can just tell it what values I want. I can type in the -3, the -2, the -1, the 0, the 1, the 2, the 3, and then there's my table right there too. Okay, if you like, that'll save you some time. All right. Alternatively, if you remember, there is a mode on our calculator for parametric though, right? If we scroll down here, there's function, right? That's what we would normally use, but then there's par for parametric. All right. And so we can type in our x and y. So 0.5, now my x button is a t button because we're in parametric. Okay, and then t squared minus 4. And now when I go to my table, you can see there your different t values and then your x and y your parameter values and then your x and y respective t's. All right, these go, wow, from -3 to 3. I guess that's because it's the same values I used earlier, I guess, right? Yes, okay. Whoops, going crazy here. There you go. So you can also do it that way too. Okay? And then the nice thing with your graphing calculator is it can graph it for you. All right, and there's somewhat. But that's not what we end up with if you actually graph these points. Let's go back to here, and then I'll come back to what's going on there. All right, so negative 4.55, so 1, 2, 3, 4 and a half. 1, 2, 3, 4, 5, right there. That's t equals negative 3. All right, and then we'll do 2, 0. Interesting. Okay, and then 2.5, negative 3. 2.5, negative 1, 2, 3. 0, negative 4. 0, 1, 2, 3, 4. And then negative 2.5, negative 3, negative 2 and a half, negative 1, 2, 3. So you see some symmetry kind of happening here. Oh, that's a 1 now, not a negative 1. And then let's see here, negative 2, 0. T equals 2. And then t equals 3 is 4 and a half. 1, 2, 3, 4 and a half. 1, 2, 3, 4, 5. T equals 3. So this is a more complicated connect the dots than maybe you were, maybe than you're used to, right? But it's the same idea, right? It's just like back when you were doing them in those like highlights magazines or whatever. You go from the number, you just connect the successive numbers here.
Is this like the ribbon?
Okay.
Oh.
Again, we know that because of the orientation, right? We want to connect successive, or
Close by, but it's
chronological points. Right? Now, when I graphed that, we got this, right? But when I graphed on my calculator, I got like half of that. What's the deal? Well, you have to go to your window. If you look here, my t minimum is 0. So you have to imagine that we're starting at t equals 0, and then we're going on to, well, in this case, they go up to 2 pi. I'm not sure why it's 2 pi, but anyway, there it is. So it's going to give you this piece, and then that's why we see only from t equals 0 on around to that. But if we want to include from negative 3 to 3, well, that's easy. We just change our t min to negative 3, our t max to 3. Our t step, we want to be 1, because that's what we counted by. And then we'll graph, and then voila.
Alright, that's dope.
There it is. Okay, on our graphing calculators.
a metal.
Yeah, there you go. Yeah. Okay. We can also, if you want to, so you can see here it gets a little herky-jerky. That's because we only counted by ones. If you make your t-step something small at a smaller increment, it'll give you a nice, smoother curve because it's only calculating, these number of points. But if we maybe do 0.1 as our step, well, now it's going to, calculate many more points, right? And so it makes a nice, smooth curve there. Oops, sorry, you can't see. There's a nice, smooth curve version of it. Okay.
Would these be calculated?
Not necessarily, right? Could be to help speed things up, but not necessarily. All right. So let's go ahead and do this one here. It says sketch the following parametric equation, including orientation and labeling. So I'm going to go ahead and set the table for you, and I'll let you guys go ahead and take this one away. There's only 4 points you'll have to evaluate here, so it won't be so bad. Okay, so 0, pi over 2, pi, 3 pi over 2, and we'll go up to 2 pi, right? Hopefully it will repeat itself after that point. So go ahead, see what you come up with.
It's a circle.
It's a circle. Is that your answer for all of these?
Well, maybe
It's a good guess. It's a good guess. Again, kind of right. There's circly aspects to it. Oops. Okay.
So you got 4 and 3. Have you studied the vocab? Have you studied the
A
vocab?
little bit, but not too much.
Okay.
That's okay. How about you?
Nope. I don't even know what any of the words are. Yeah, I played Fortnite last time first.
Oh, I didn't use the 3 here.
Yeah, once I took that calculus test, I was like, yo, that was cool.
Is it an oval?
What's
Is it a
that?
diamond?
Ellipse is what I would say, if you like make it rounding. Yeah.
Said it, Mario.
I don't know if oval has a mathematical definition, but ellipse does. I know that. So,
Good job, buddy.
So an oval.
so an oval, exactly. All right. So oval. There it is. All right. It is a oval or ellipse. All right. A smooshed circle. Okay. So there's that. And we'll stop there. We have one more to look at here. Again, it's like more of a word problem kind of thing. But we'll cover that
No homework, right?
when we get there on Monday. So no, the homework will be posted to Google Classroom. Okay. Don't forget, you also have a problem set, right, that you want to continue to be working on.
Aren't we about to run out of things in the book? Aren't we near the end of the book already?
Well, so we skipped a chapter, and we're going to come back to that chapter after this chapter. So we're in chapter 10 right now.
Yeah.
We're going to go back to chapter 9 here.
How many chapters are there?
10.
10.
Yeah, 10.
So we only have 2 more units to learn? And that's it?
And the next unit, yeah.
Yeah. Well, I think we split up. The prior unit because, like, the unit we skipped. We split that up into 2 things because it's pretty intense.
What's the unit?
Sequences and series.
So wait, we'll still have
That sounds familiar.
It's like when I was talking to Mr. Goff last year about potentially teaching ABBC, I was like,